when we talk about the Gibbs energy, right? Now Gibbs energy is a very important parameter, right? Very important parameter, which tells us that if the reaction is spontaneous or not, right? Got it? Now, if the reaction, if the Gibbs energy is negative, what does it tell you? The reaction is, tell me, spontaneous, right? Understood? Spontaneous, right? Fine. And the reaction is moving in the, tell me, if the reaction is spontaneous, which direction is moving? Forward or the backward? Which direction is moving? Tell
Forward.
me. Forward, right? Clear? If the Gibbs energy is positive, means the reaction is non-spontaneous. What does the non-spontaneous reaction tells you? The reaction is moving at the, tell me, backward
Backward.
direction. Backward direction. So in any reversible reaction, we can judge that which direction is moving by the Gibbs energy, right? And if the Gibbs energy is zero, the reaction is at equilibrium. This bit is very important, right? This bit is very important. Got it? Get my point, right? Understood, but reaction is at equilibrium, right? Clear?
Yeah.
Now coming to this part, you have to see that when we talk about when we talk about any suppose the equation, right? Delta G reaction is equal to what? Delta G reaction is equal to the Gibbs is the product minus Gibbs is the reactant, right? This is the equation we know, right? Understood. Now suppose we have taken a fully charged lead battery, right? Lead acid battery, right? Fully charged, and put a bulb. Understood. Now at the start of the reaction, there will be reactant only. Understood. Understood. There'll be reactant only, right? Now, if you see when we talk about the Gibbs energy, right? Gibbs energy is what? Gibbs energy reaction is what? Gibbs energy product. Total Gibbs energy product minus total Gibbs energy reactant. Suppose we are taking a fully charged lead battery, right? Fully charged. So at that time, what happens? Only reactant is there. Understood. Understood this part. So GR will be very high. Understood. And GP will be zero. Understood this
Yeah.
part, right? So at that time, what happens? The Gibbs energy will be very negative, highly negative, right? Understood. Understood this part. Now, as the reactant gets transferred to product slowly, what happens? That what happens? The GP increases slowly. Understood? Slowly,
Yeah.
right? This increases. When this increases, what happens? The negative value of the Gibbs energy will be coming down slowly. Understood? Will be reducing, right? Isn't it? Understood?
Yeah.
We know that if the Gibbs energy is more negative, more work can be extracted from the system. This is a very important part here to link now, right? Gibbs energy tells us spontaneity. Agreed. But Gibbs energy tells you that about the work that can be extracted from a system, right?
Yeah.
More negative with the Gibbs energy, more work that can be extracted from the system, right? Clear? Do you get my
Yeah.
point? So it will be going from what? More negative to less negative, less negative. That will be seen in the bulb also, right? The bulb will be growing brightly at first. Work generated from the system. See, Gibbs energy tells you the work that can be obtained from a system, right? It
Yeah.
will be going less negative and less negative. Mean the bulb will be glowing less brighter, less brighter. That also will be shown by the experiment, right? Clear? Get it? Is it clear to you? Understood this part? Now, at a particular time, when the product's Gibbs energy will be equal to Gibbs energy of the reactant, the Gibbs energy of the reaction will be equal to zero, right? And the bulb will be now switched off. There'll be, isn't it? Bulb won't glow, isn't it? At this point of the time, we can tell that the reversible reaction had come in equilibrium and no work can be extracted from the system, right? Clear? So when Gibbs chain is equal to zero, we can tell what? We can tell that no work can be extracted from the system, right? And the
Yeah.
reaction is at equilibrium. Got it? Is it clear to you? Did you get my point, right?
Yeah.
This Gibbs chain the reactive is very high. So this will be very negative. When it transferred to the products, right? What happens? This starts to increase, right? And this starts to decrease. So the negative value of the Gibbs energy will be coming down slowly, right? And the bulb will be glowing less brightly, right? Isn't it? Can you read? Can you read? Can you see? At the start of the reaction, the total Gibbs energy of the reactant is greater than that of the product. So a lot of work is available, and Gibbs energy is more negative, and the reaction moves in the forward direction. As the
As the
battery
back.
discharges, the
Yeah.
reaction continues to convert reactants to products, right? So the total free energy will decrease. Free
Yeah.
energy is the amount of work that can be extracted from the system, right? And
Yeah.
less work is available, right? Clear? You get my
Yes.
point?
Yeah.
Understood? Do you get my
Yes.
point, right? Now over here you have to understand that now write down quickly. You'll be getting a graph like this, right? Always try to see that at equilibrium, write down at equilibrium, right? At equilibrium. This point you write down. GP and GR, right? Both will be at their minimum value. This is very important, right? Minimum value, not zero. GP and GR will be, the differential product and reactant will be at the minimum value. Can you see this? Isn't it? Is there minimum value? This is a reactant. This is a product here at the minimum value. Second, at equilibrium, GP will be equal to GR, right? Clear? At the minimum value. Third, the entropy will be maximum. You write down this, right? Clear? This bit you understood, right? Do you get my point? Do you get my point? Is
Yeah.
it clear to you? Again, I'm telling you, at equilibrium, what happens? GP will be equal to GR, and they both will be at their minimum value, right? Not zero, at their minimum value, right? And the entropy will be maximum at equilibrium, right? Maximum degree of disorderness, right? Clear? Do you get my point? Fine. So that's the point. Now coming to the part, you'll be seeing that if you see that delta G is equal to minus RTL and Kc, we can write down this reaction, right? Understood?
Yeah.
This is clear to you, right? Just give me
Yeah.
1 minute, right? Just 1 minute, 1 minute, 1 minute. Huh?